Today, our focus is going to be on the fact that not all equations are easy or efficient to solve with inverse trig. I hope that you thought that the way that we solved the equations in the first part of this section was pretty easy and pretty quick. To show you what I mean about not all equations being easy to solve with inverse trig, I want to consider this equation. The directions are the same that you saw in the first part of the section, solve on the interval 0 to 360 degrees. We will use radians later today. And the equation looks familiar, 5 cosine theta plus 3 equals 1. To start solving this equation, I isolated cosine by subtracting 3 and dividing by 5, and got that cosine was equal to negative 2/5. Then, since that wasn't a cosine value I was familiar with, I went to my calculator and did inverse cosine in degrees and got 113.58. Now, unlike the angles that you got from your calculator in the first part of this assignment, 113.58 is not the reference angle for our solutions. It is, however, the second quadrant answer to this equation. Since cosine is negative, we should be expecting two answers, one in quadrant 2 and one in quadrant 3, which comes from ASTC. But something that didn't come up in your first assignment is the idea that I mentioned in our first video, which is that inverse cosine of a negative number gives an answer in quadrant 2, not quadrant 4, like inverse sine and inverse tangent. And that's because for cosine, the quadrant that is closest to 0 with negative values is actually quadrant 2. So inverse cosine gives answers between 90 and 180, like 113.58. The problem is, because that's a second quadrant angle, we don't know the reference angle. If it was in first quadrant, the reference angle would just be that angle. And if it was a negative fourth quadrant angle, it would just be the positive version of that angle, like you saw in your last assignment. So to get the second solution to this equation, we would first have to find the reference angle for 113.58 by subtracting it from 180 to find the space between that blue angle and the negative x-axis, which is 66.42. And then we'd have to realize that we want our second solution in third quadrant, so that's also going to have a reference angle of 66.42 because all angles whose cosine is negative 2/5 should have the same reference angle. And then to find the actual answer angle, we'd have to add 66.42 to 180 to get 246.42. So we got our final answers without a lot of work, but it can be very tempting to forget that you don't know the reference angle when you do inverse cosine of a negative, and it can be very easy to make a mistake with finding that second solution. Another time solving using inverse trig can be kind of confusing is if you have to solve your equation in radians. So in this example, I changed the directions from solving on 0 to 360 to solving on 0 to 2 pi, which signals your answer should be in radians. So just like our other examples, I started by isolating tangent. Then I changed my calculator to radian mode, and I did inverse tangent of negative 4/3, which gave me negative 0.92. Because we're used to seeing radians written as a fraction times pi instead of multiplied out into a decimal form, it's hard for us to visualize what negative 0.92 radians is. In order to visualize it, I took my coordinate plane and I marked it off in terms of 0, pi over 2, pi, 3 pi over 2, and 2 pi, but I also converted each of those to decimals, which I just did on my calculator. So the pi over 2 marker is 1.57. So that means that negative 0.92 is going to be in the fourth quadrant because it doesn't get all the way to negative 1.57. To finish solving this equation, we'd have to remember that what that negative 0.92 tells us is that our reference angle is going to be 0.92. Because tangent is equal to a negative value, we know we're going to want two solutions on 0 to 2 pi, one in second quadrant and one in fourth quadrant. We can't use the negative 0.92 as one of our answers because it's negative and 0 to 2 pi only includes positives. So what I did to rewrite that fourth quadrant answer was I did 6.28 minus 0.92 to get my 5.36. And then I moved that reference angle of 0.92 up into the second quadrant, and I knew that I had to get that second quadrant value, so I did pi, or 3.14, minus 0.92 to get 2.22. So again, it's not a ton of work to solve these equations in radians with your calculator using the same method we knew, but it can get a little confusing, especially trying to visualize what your quadrants need to be and knowing what decimal you need to subtract from, etc. So what I want to talk about in this video is that there is another way that you can use on your calculator to solve these equations that many of you, I think, will probably find easier and much more useful going forward. The easier method we're going to talk about is using a graphical approach. And by that, I mean solving an equation by graphing. As an example, we're going to redo the problem we just did. When I say take a graphical approach, this is what I mean. I mean that we're going to take the two sides of the equation, the 3 tan theta plus 5 and the 1, and we're going to graph them as two separate functions. You can graph the first half as f1 of x and the second one as f2 of x. It doesn't really matter which one you do. Then you're going to find the intersection points of those two functions, And the x values of those intersections are going to be the angles on 0 to 2 pi, where 3 tan theta plus 5 equals 1. We'll try it. Graphing calculator, I'm going to add a graphing page. And I see that my graphing page is already in radians, which is what I wanted for this problem. If it wasn't, I would need to change into degrees, which I could do by hitting menu and then settings, and I could change my graphing angle to degrees. But for this problem, I'm okay. So then I'm going to type in my equation, 3 tan, and you can't write theta in the graphing page, you have to use x, and then plus 5, and I'll hit enter, and I see something that looks like a tangent graph, so that's good. And then I'll hit tab to bring up the graph entry line again and type in 1 for the second half of the equation. We see there are a lot of intersection points. So this is representing the infinite number of places where 3 tan x plus 5 intersects with 1, or the solutions to our equations. To find the answers, I'm going to use the Analyze Graph tool and intersection. And I'm going to intersect these graphs, and I see 2.21, which matches up with the 2.22 I found by hand. It's probably just off because of rounding. And I know I should get a second solution, so I'm going to look for the next one. And by the way, I started with this one because it was the first one that came to the right side of 0. My second intersection is the 5.36 I was expecting. And we know that there should be 2 solutions on 0 to 2 pi from our previous work. But if I wanted to prove to myself that I didn't need any more intersections in this interval, I could find the next one. And the x value of that, the angle that we're looking for, is 8.50 radians, and that's bigger than 6.28 or 2 pi, so that wouldn't be an answer to our equation. However, we know there are infinite answers to these equations that you might want in some context, and a graph makes it really easy to see all of them and find as many of them as you possibly want. So the final answer to this equation is 2.21 and 5.36, and those are the x values of the intersection points. Solving by graphing is particularly useful if you have very complicated trig equations. We're going to end with this example. In the scenario below, find the first time after midnight when the rate that the fish are entering and leaving the lake are equal. We're going to assume that the e of t function is written in radians. And so the given information, the scenario I'm talking about, is it says that fish enter a lake at a rate modeled by the function e, which is e of t equals 20 plus 15 sine pi over 6, that's the key that it's in radians, times t. And then it says fish leave the lake at this other function L, which is 4 plus 2 to the 0.1 t squared. And they're both measured in fish per hour, so they're rates. And t is hours since midnight. So what this is really asking us is to find out when e of t and L of t are equal. So we need to solve 20 plus 15 sine pi over 6t equals 4 plus the exponential 2 to the 0.1 t squared. So this looks really complicated, but not if you think of it from a graphical perspective. We can just take one side and graph it as f1, take the other side and graph it as f2, and intersect them to find our solutions. So now I'm back to my calculator, and I'm going to add a new graphing page to do this second problem. And since I already am in the same document, my new graph is going to come up as f3. So I'm going to type in 20 plus 15 sine, and then I'm going to make a fraction. And I'm just going to type in, instead of using the pi symbol, you can just type in pi times x. We can't use t, and that's over 6. And I'll graph that one. And again, I'm already in radians, so this is good. And then I'm going to hit tab to bring up my entry line, and I'm going to type in the second function, 4 plus 2 to the 0.1, and I have to remember to use x, not t squared. And I can see that there are definitely going to be some intersections for these graphs, but I can't quite see them. I know I want some more in the y direction, so I'm just going to change the y max value maybe to 20, and if that's not big enough, I'll make it bigger. No, this looks like it's pretty good because I'm looking for the first intersection after 0, and I can see that to the right of the y-axis, I can see an intersection right here. So I'm going to use my intersection tool, and I can see that the x value of that intersection, which is going to be our t, is 6.20. So that means that at 6.2 hours after midnight, the fish were entering and leaving the lake at the same rate. So one thing I'm hoping that you can take away from here is that for really any equation, I'm reminding you about this in the context of trig, but it can be applied in many other places. It does not matter how complicated an equation you have, graphing is always a very easy and efficient way to get answers, especially in complicated situations. So when I saw this trig equation equal to an exponential, I said, oh, I'm just going to graph, find myself a good window, make sure I'm in radians versus degrees, and I'll be able to find an answer really easily, not trying to deal with any algebraic methods or having to remember any rules.